In this video, we gonna talk about the comparison test and limit comparison test. The first test that we're gonna study is called the comparison test, and the comparison test turned out to be used only for the series with non-negative term. So the important assumption that you see here is gonna be this guy can be used only for the series with non-negative term. So you'll not be able to use this test for the series that you know that some terms are negative. Okay. The thing behind the idea of the comparison turned out to be if you like to conclude that the series AN is convergent. If you like to conclude that the series AN is convergent, so your point turned out to be your AN here. So if you like to conclude that your series is convergent, you're gonna find a larger sequence. Okay, so it's going to be you have the series, not sequence, so it's going to be you have AN and you're going to find a larger BN. So BN in this case is larger than AN, and if you know that the series of the larger term, okay, so you have the series of AN and you have the series of BN. And if you have the series of the larger term turn out to be convergent, the smaller one turn out to be convergent. So by comparing, okay, so that's why we call this guy comparison test. So you have series AN smaller than series BN, and this guy conversion. So you're gonna be able to conclude that the series AN conversion. Okay, so that will be the first idea. And the second idea will be if you like to conclude that your series is divergent. So you have the series higher than the series that divergent. Okay, so you see the first case that you have the term that turned out to be smaller and the bigger one or the larger one is conversion. So you have the smaller one is conversion. And if you have the larger one, so if you have some AN higher than some BN, okay, so if you have some AN higher than some BN, and you know that some BN turn out to be divergent, so you'll be able to conclude that the series that bigger, okay, so it's going to be some AN is divergent. Okay, so that is going to be the conclusion that we can reach. Okay, so it's going to be 2 points that we're going to aim for. So the difficult part or the hard part turned out to be you need to find BN on your own. So you need BN, okay, so you have to find BN on your own. Okay, so you're gonna have to find BN on your own. Okay, so you find this guy on your own and you're gonna have to use the thing that we kind of know the result easy. So it's gonna be the series to the n. Okay, so this guy is called geometric series. So this guy is convergent when you have absolute R smaller than 1, and it's going to be divergent if you have absolute R greater than or equal to 1. So this is going to be the first thing that you use. Another thing is going to be the series Bn can be P series. So it's going to be 1 over n to the P. And this P series gonna be convergent if you have P greater than 1 and it's going to be divergent if you have p less than or equal to 1. Okay, so that is going to be two kinds of series that we use. So this guy is called geometric series. The second guy is called P series. Okay. So this one is kind of difficult to use. Okay, we study this one first. However, this one is not gonna be the first one that you're gonna use. It's gonna be kind of the last one when you're not be able to do something else. So for this one, we're gonna do the first example. The first example, you have your AN here. Okay, so you have your AN here. AN equal to sine square n over n to the third here. So in this case, you're gonna look at sine square, and we know that sine square n, okay, sine square n always less than 1. Okay, so for this one, we learned this one before, that you have sine n less than or equal to 1. So you have sine square is less than or equal to 1. And you see that this guy over n cube will be over n to the third here. So you reach the conclusion that you have sine square n over n to the third less than or equal to 1 over n to the third. And this one will be your an. And this one will be your bn. Okay, so this one will be your an and bn. And you know that since the series 1 over n to the third converges. Okay, so because we know that the larger one, okay, so this one is larger. So you know that the larger one is conversion. So you can conclude that this smaller one turned out to be conversion. Okay, so it's gonna be, you have the smaller one, which is series sine square n over n to the third converges by the comparison test. Okay, so that will be how we conclude that the series is convergent. You may feel that, hey, it's not that difficult. It's difficult because this one you have to create Bn. Okay, so Bn must be created on your own. Must be created by ourselves. Okay, so this one kind of difficult because how would I know that it's going to be Bn equal to 1 over n to the third? Can you use something else? Actually, this one is gonna come from the structure of the series that you see. So you see that you have to know some algebraic property of the trigonometric function psi, okay? And you use this kind of test in order to find the B series Bn. And how would you know that it's gonna be smaller or bigger? Okay, so how would we know that it's gonna be A or B? You don't actually. So A or B is going to depend on the algebraic expression that you see from the series. Okay. For the next one, you see that you have arctan n and you have n. And if you recall the graph for arctan, if you recall the graph for arctan, it's gonna turn out to be an S-shaped curve here. And the picture turned out to be like this. That gonna tend to pi over 2. Okay, so you have this guy and you have the horizontal asymptote is pi over 2. And you see that you're gonna have 1, 2, 3, 4, and so on. So you see that you have 1, okay, you have 2, 3, 4, and you know that, hey, can we just have arctan n less than pi over 2? It's correct, right? So you have arctan n less than pi over 2, and you know that it's gonna be arctan n over n will be less than pi over 2 times 1 over n. Okay, so you divide by n both sides. This is what you get. You may confuse. Let me write this way. So it's going to be pi over 2n instead. Okay, and you're gonna get the series arctan n over n smaller than the series pi over 2n. Okay, and for this series, you'll be able to move pi over 2 out. So it's going to be pi over 2 series 1 over n. And hey, this one is p series, you recall, right? So this one is p series or harmonic series. So this one, you have p equal to 1. Okay, so it's going to turn out to be divergent. Okay, so this guy is turned out to be divergent. And you see that you have this guy, the series AN. Okay, so this one is your series AN. So you have your series AN smaller than, okay, so let me enlarge this one and I have my AN. So I have my series AN smaller than divergent, okay? And you see that, hey, if it turned out to be divergent, it must be larger than, so we be able to reach the conclusion. However, in this case, you see that you have this guy smaller than series that divergent. So you not be able to conclude anything yet. Okay, so that's why I call that this guy kind of not easy to do. So it's going to be no conclusion. Okay, so this is, you did this one by your instinct. So if you do it this way, you're going to reach no conclusion. Okay, so I'm going to keep this to remind you. Okay. However, you can do another way. You see that your graph arctan. Okay, so this one is your arctan. So your graph arctan, you know that your arctan n, okay, will be higher than arctan 1. Okay, so you see that you have arctan 2, arctan 3, arctan 4, and so on. Everybody is greater than, actually it's going to be greater than or equal to arctan 1. Okay, so arctan n greater than or equal to arctan 1. And what is arctan 1? Arctan 1 is pi over 4. Okay, so it's pi over 4. And you do the same thing. So you get arctan n over n gonna be higher than pi over 4n. Okay, and you see that this series, so you get arctan n over n is gonna be higher than the series pi over 4n. Okay, so this guy will be pi over 4 series 1 over n. Okay, so you see that, hey, we reach almost the same, but we have the inequality in a correct direction or in the correct sign here that we like to have. So for this one, okay, so for this one, this guy is divergent. Okay, so this guy is divergent, and this series is higher than the divergent series. Okay, so this series is higher than the divergent series. So you reach the conclusion that the series arctan n over n is divergent by comparison test. Okay, so the hardest part that you have for this test is going to be you have to find the series Bn on your own. Okay, so you like to find this guy on your own, and if you be able to find this one, it's going to be you'll be able to reach the conclusion. Okay, so it's depend on the situation that you're gonna be able to have your series higher than or less than. If it's higher than divergent series, it's gonna be divergent. If it's smaller than a convergent series, you're gonna have its conversion. So that will be the key idea. However, the difficulty for this guy is going to be you use your algebra, your knowledge in algebra in order to find the thing that you have. Okay, the next one for number 3 is going to be 3n equal to 1 to infinity of 1 over 3 to the n plus 1. So for this one, you know that you have 3 to the n plus 1 always more than 3 to the n. Okay, so this is just basic one, so it's going to be plus 1 and not plus 1, so on the plus 1 side will be more than. And you see that if you flip this one, the inequality turn out to be opposite. Okay, so it's going to look like something nice like this. Okay, and so you have the series. Okay, so you have the series 1 over 3 to the n plus 1 smaller than the series 1 over 3 to the n. And you must recall that this guy turned out to be 1/3 to the n, and this become a geometric series. Okay, so this guy become geometric series with r equal to 1/3. Okay, so with r equal to 1/3. So this guy is convergent. Okay, so this guy is convergent. So you see this series that given in the question is smaller than this series, which is convergent. So you're gonna be able to conclude that the series 1 over 3 to the n plus 1 is convergent by the limit comparison test. Okay, so that, sorry, it's gonna be by comparison test. We don't have limit comparison yet. By the comparison test. Okay, so this one is gonna be just this one is smaller than the one that conversion, so it's gonna be conversion by comparison test. So you see that this one we use geometric series before we use P series. Okay, so the next one again, so you have log n, okay, log n over root n, okay, so log n over root n, and you know that you have log n can be two ways, same thing. So if you record the graph of log, okay, let me shoot. I like to erase, sorry. So for number 4, you have log n over root n. So for this one, if you record the graph of log, so you would get y equal to log x is gonna be like this curve. Okay, so y equal to log x. Okay, so this one will be your x, will be your y. Okay, and you see this one is log 1 is equal to 0, and log 2, okay, somewhere log 3, 4, 5, and you see that log 2 is here, log 3, okay, and so on. So you see that from this you get log n is more than or equal to log 2. Okay, so log 1 is 0. Okay, this guy is log 1. Okay, so you see that log is an increasing function. So you have log 1 is 0, log 2, log 3, and it's going to continue increasing. So you have log n higher than log 2, higher than log 1, and you like to have log n over root n. So you divide everything by root n. And so you take the series. So it's going to be log n over root n log n. So it's going to be log 2 over root n. And log 2 is constant. Okay, so log 2 is just constant. So this guy will become log 2 series 1 over root n. Okay, and so you would get, okay, so you would get this series, and if you take a look at series 1 over root n, okay, so you get series 1 over root n. This guy is a p series with p equal to 1/2. Okay, so p series with p equal to 1/2, so it's gonna be divergent. Okay, so it's turned out to be divergent. So you're gonna have the series log n over root n higher than divergent. Okay, so this is the thing that you may write down. So it's gonna be log n over root n higher than divergent. So you get the series log n over root n is divergent by comparison test. Okay, so it's going to be by the comparison test. Okay, so that is going to be just this one. Okay, so it's going to be if you be able to find Bn. Okay, so and I told you that the difficulty for this guy turned out to be you need to be able to find Bn correctly. Let's do number 5. Okay, number 5 is going to be series n equal to 1 to infinity of 1 over in fact. Okay, so it's gonna be 1 over in fact, and you're gonna have for this one, if you look at in fact, 1 over in fact, so it's gonna be 1, and everything will be over. Okay, so it's gonna be over 1 times 2 time until time n minus 1 time n. Okay, so 1 times 2 times n minus 1 times n. And the thing that you see here is gonna be, if you just ignore this part, okay? So if you compare this one with, okay, so I can just ignore this part. So it's gonna be n minus 1 times n, okay? And you see that you have 1 times 2 disappear, okay? So you see that for this term and for this term, okay, this one is going to be more than, okay, so if you compare this one for me a little bit, so you have 1 times 2 times n minus 1 times n. This guy will be more than n minus 1 times n. Okay, so will be more than n minus 1 times n. And you see that if you flip this one down, so it's going to be 1 over 2 n minus 1 times n. Okay, it's going to be more than 1 over n minus 1 times n. Okay, and you see that the greater than will be the sign that we must put here. Sorry, smaller than. Smaller than. So this one you flip, so you get this guy, okay? And you see that, hey, it's gonna turn out to be something nice like this one, okay? So it's gonna turn out to be 1 over n minus 1. And this one will be our bn, okay? So this guy will be our bn. Okay, so let me move this calculation a little bit. So it's gonna be this term. I will put it up here. Okay, so you're gonna find the conversion. Okay, so show. Okay, so we must show that the series 1 over n minus 1n is conversion. If you be able to show that this series is conversion, you'll be able to conclude that, hence by the comparison test, we can conclude that, okay, so we can conclude that the series 1 over n factorial is also conversion. Okay, so we can conclude that the series is also conversion. Okay, so I let you do this one on your own. Okay, so I will let you do this one on your own. So this one, I hint you that use telescopic sum. Okay, so use telescopic sum. Telescopic sum is on page 14, example 12. Okay, so you're gonna have to go back to example 12. So example 12. Okay, so I let you do this part first, and then I show you during the recitation. Okay, so this one will be number 5. So you see that it's kind of tricky to get AN and BN. Okay, so you have your AN, this part. Okay, so you have your AN and it's kind of a little bit tricky for getting BN for using the comparison test. Like I told you, it's not quite easy. And for the last one, okay, this one is also not quite easy, okay. So you see that this guy is n plus 2, okay, minus log n, okay, so n plus 2 is minus 2 log n. So this one, okay, the tricky part turned out to be, you notice that n plus 2 is greater than or equal to 3. Okay, n plus 2 is greater than or equal to 3. Why? Why? Because we know that n higher than 1. Okay, so we have n plus 2 is more than 1 plus 2 equal to 3. And 3 is more than E. E is about 2.718. Okay, so E is about 2.718. So you get N plus 2 higher than E. Okay, so this is the thing kind of tricky. So we just use algebra. However, the algebra here is not quite natural. And you're gonna raise to the negative 2 log n. So you need this yellow guy. Okay, so it's gonna be n plus 2 minus 2 log n. Okay, higher than e to the negative 2 log n. Okay, so this guy is the yellow guy. Okay. Why this one is nice? Because if you recall, okay, we be able to simplify this term. Okay, so we be able to simplify this term into something kind of nice. So this guy turned out to be e to the log n to the negative 2. Okay, and e and log will cancel each other. So this one is just n to the negative 2. Okay, so it's going to turn out to be n to the negative 2. So you get n plus 2 negative 2 log n higher than 1 over n squared. Okay, so it's higher than 1 over n squared, which is n to the negative 2. And you see that you take the series both sides, n plus 2 negative 2 log n will be higher than the series 1 over n square. Okay, and this one is p equal to 2 more than 1, so it must be conversion. Okay, so it must be conversion. Okay. I make some mistake, and it's important mistake. I have negative. Okay, so this one is incorrect. I forgot to mention. Okay, let me fix my mistake. So here I have negative side. Okay, I have negative side. Okay, I have negative side. I have been too fast on this one. Let me move this one down a little bit. So the thing that before I have negative side, I should just have positive side. So it's going to be n plus 2 to the 2 log n will be more than e to the 2 log n. Okay, so you raise to the positive power. So this one is positive. Okay, so it's turned out to be okay. However, if you have negative, it means that you flip this one down. Okay, so it means that you flip this one down. So it's gonna be negative, so it's going to be not negative, it's going to become the opposite side. So the opposite side result in something like this. Okay, so it's going to be resulting in this guy. So I highlight this one and I highlight this one. So you see the difference here is going to be this one is positive side. Okay, when you have negative side, it's going to be 1 over and 1 over. And when you have 1 over and 1 over like this one, it's going to flip the side for you to negative side. Okay, so this one I make mistake, sorry. And you see that this guy turned out to be conversion, and this guy is your AN. Okay, so this guy is your AN. So you have your series turn out to be smaller than the series that conversion. So you must have the series is conversion by comparison test. Okay, so this one will be the final conclusion for number 6. Okay, so we did many examples. So the thing that I would think that you'll be able to follow me so far. However, the difficult turn out to be you have to create BN on your own, and it's gonna come from practice. Okay, so you not be able to get this one right away when you see that. How would I know that it's gonna be comparison test? The comparison test come from you not be able to use other tests. Okay, so that is gonna be one thing. Okay, so you see this one is called comparison test, and sometimes we face with the series that the comparison test fail. For example, you look at number 3 again. Number 3, you see that you have 3 to the n plus 1 higher than 3 to the n, and you'll be able to have everything set up nicely in terms of comparison test. However, if you look at example 22 here, you see that it's going to turn out to be 2 to the n minus 1. Okay, so for this one, it is 2 to the n minus 1. And when you have 2 to the n minus 1, you get this guy smaller than 2 to the n. And when you flip this one, so you get 2 to the n minus 1 higher than 1 over 2 to the n. And you know that the series 1 over 2 to the n is conversion, because this one are equal to 1/2, okay, less than 1. So you have that this guy is conversion, okay, so this guy is conversion, and you see that, hey, this guy is conversion, and this one turned out to be higher than, we not be able to reach the conclusion. Okay, so we not be able to reach the conclusion. How would we test whether this series is conversion or diversion? So the comparison test fail. Okay, so the comparison test So what will happen if the comparison test fail? The thing that we can use is going to turn out to be something close to the comparison test. It's going to call limit comparison test. The limit comparison test turn out to use the sequence Bn. However, you don't have to know algebra. So you don't have to use algebra for comparing two terms. It's going to be if you feel that you be able to compute limit n go to infinity of this term an over bn. Okay, so we find, okay, we will find Bn such that this limit, okay, so let me use other color, sorry, it should be we will find Bn such that, okay, so we will find Bn such that you be able to compute this limit, and this limit turned out to be positive. Okay, this limit turned out to be positive. If limit equal to 0, you'll not be able to conclude anything. Okay, so if limit equal to 0, you'll not be able to conclude anything. So you'll be able to conclude only for limit higher than 0. And the conclusion would be you have either series converges or this guy both diverges. So what does it mean? It means that if you like to test an, you find Bn such that you have this limit is more than 0, it's going to be limit an over Bn. So if you have the series Bn convert, okay, so if this guy convert, An will convert. If you have Bn divert, An will divert. Okay, so that is going to be our conclusion. How would this one easier than the previous one? It's going to come from the thing that you need to do. It's not going to involving inequality. And it's going to involve only the structure of the function. Okay, so phi Bn, okay, so I'm going to tell you about the trick that the trick for finding Bn turned out to be, okay, for, okay, we're going to use the structure of Bn not of Bn, of An to find Bn. Okay, I will explain what this one means. Okay, so you see the structure of your An here. Okay, you see the structure of your An here. An is 1 over 2 to the n minus 1. So we choose Bn. Okay, so we're going to choose Bn to be the one that's similar to An. So it's going to be 1 over 2 to the n. Why did I choose this one? Because when you compute the limit n go to infinity of An over Bn, okay, so when you compute limit n go to infinity of An over Bn, you'll be able to do it. So it's going to be limit n go to infinity of 1 over 2 to the n minus 1 over 1 over 2 to the n. And this guy is going to be some simplification. So it's going to be limit n go to infinity of 2 to the n over 2 to the n minus 1. Okay. And you can use L'Hopital or you can just use your algebra. So you see that this guy is 2 to the n and you have 2 to the n outside, 1 over 2 to the n. And you see that you can get rid of 2 to the n and you have n go to infinity. This guy turn out to become 0. Okay, so you'll be able to find this limit. And so okay, so you see that this limit turned out to be equal to 1. Okay, so this limit turned out to be equal to 1. And the thing that you be able to conclude turned out to be since the series Bn, okay, series 1 over 2 to the n converges. Okay, so you have the series Bn converges. You're gonna be able to conclude that the series 1 over 2 to the n minus 1 converges. Okay, so that is gonna be how we conclude for this limit. Okay, let me uh, let me explain this one again. So you begin with an, you choose Bn that structure similar to an in the way that you be able to compute the limit of the quotient of an over Bn, and this limit turn out to be not equal to 0. Okay, if the limit turn out to be equal to 0, you have no conclusion. It's gonna be limit equal to 1 that higher than 0. Let me emphasize on that term also. Okay, so this one is positive. Okay, so the thing that you also need, okay, so the thing that you also need is gonna be, we also need the following fact. So we also need the following fact. What kind of fact that I need? It's gonna be if you compute limit n go to infinity of ak, okay, n to the k plus ak minus 1 n to the k minus 1 plus until a 0, okay, over if you have bm n to the m plus bm minus 1 n to the m minus 1 plus until b0, okay. This limit of the quotient between two polynomials is gonna turn out to be equal to the ratio ak over bm if, okay, so it's gonna be ak over bm if you have k equal to m. Okay, so it's gonna be this ratio, and this guy turned out to be not equal to 0. Okay, so it's turned out to be not equal to 0 when you have k equal to m. And if you have the denominator, more than m, okay, so if you have k more than m, it's turned out to be infinity. Okay, so it's gonna turn out to be infinity or negative infinity. So I'm gonna just say diversion. Okay, so it's gonna be divergent if k more than m, and it's gonna be 0 if you have k less than m. So the important one turned out to be the first case. When you have k equal to m, so if you have this term and this term, the thing that you must try to find in order to find the limit of the quotient turn out to be not equal to 0 must be you need the power of the numerator and the power of the denominator to be the same. Okay, so this is the key idea that we gonna use, and this one just come from L'Hopital, so you'll be able to just differentiate k time on top and on the bottom. You're gonna reach the conclusion. Okay. Okay, so let's try to number 2. Okay, before I do that, let me give you some example. If I ask you to find limit n go to infinity of 2n squared plus 4n minus 1, and you have root 3n squared plus 2 like this. So you see that you have k equal to m, okay, and this limit turned out to be just the quotient between the leading coefficient, so it's gonna be just 2 and root 3, okay, so this one will be just 2 over root 3. So when you have this the same, you're gonna have this limit, and this limit turned out to be not equal to 0. Why this one is important? Because you see that I'm gonna teach you how to adjust this term a little bit. So you see this is your series AN. Okay, so we need to find Bn such that limit n go to infinity of an over bn not equal to 0. Okay, so we need to find bn such that the limit n go to infinity of an over bn turn out to be not equal to 0. So you see that you have n plus 1 over 3n squared minus n plus 1 like this. So you're gonna over something that is gonna turn out to be 3n squared minus n plus 1, and you see that this power is 2. So you will need something, okay? So you will need something, let's say Bn, that is gonna make the top to be n squared, okay? So you need something to make the top to be n squared, because we need the same power as well. So in this case, you're gonna have Bn equal to 1 over n. Why did I choose 1 over n? Because you see that if you flip this one up, this guy gonna multiply to n plus 1. So you would get n squared plus n. Okay, so you would get n squared plus n. Let me highlight with the red the multiplication here. Okay, so you see that the red multiplied with the red one on the bottom turned out to be n squared plus n. And you see that, hey, this one has a nice limit. So this one has limit equal to 1/3. Okay, so it's right. You see how did I say that I like to adjust the degree? Okay, so I like to adjust the degree to make it to be the same. So it's going to be 1/3, not equal to 0. And you have the series 1 over n diverges. Okay, so you would get the series n equal to 1 to infinity of n plus 1 over 3n squared minus n plus 1 is also diverges. Okay, so the key thing is going to be you like to adjust the degree to make the limit turn out to be not equal to 0. So you need Bn in a suitable power that when you flip the term, the red guy to the red guy on top, okay, the red guy to the red guy on top here, you obtain the same power as the bottom, okay. I will give you one more example to work on your own. Series n equal to 1 to infinity of n to the third plus 2n to the third plus n minus 1. And you have 5n to the 6 minus n squared plus 4. Okay, so it's going to be this one. Try to work on this one on your own, okay, to see whether conversion or diversion. I will give you the solution during the recitation. For number 3, it's gonna be the same thing. You see that this guy, you have an into the 1/3 minus 2, and you have the fourth root. So sorry, the square root. So it's gonna be n to the 5/2 plus, I don't know. So it's gonna be just this one. I don't care about the other term. So it's gonna be something like this. So this one is your an. Okay, so this one is your an. Okay, so you need bn. Okay, so you need bn such that you be able to find limit n go to infinity. And this limit turn out to not equal to 0. So you see that Bn must be, okay, so you see that, hey, it's gonna be n 5/2 on the bottom plus I don't care, okay? And you see on top that you have n to the 1/2 and 5/2 here, okay? 5/2 here is 2 plus 1/2. So you see that you need, okay, so this one is 5/2. So you need Bn equal to 1/n squared. And this will allow you to combine the rate term with the rate term, okay? So you have this one, and you're gonna finish this one, okay? And you're gonna sin like a series 1/n squared, okay? So we have the series 3 root n minus 2 over the square root n to the 5th plus 3n squared minus 1. Okay, so you gonna fill that conversion or diversion for me. Okay, and you find also the limit. Okay, don't forget to find the limit for me. And this one equal to what? Not equal to 0 or more than 0. Okay, so that is gonna be the conclusion that we can draw. Okay. Okay, so I let you find this one on your own to practice. Okay, so you have many examples here. So you have this guy, okay, that we're gonna discuss during the recitation. Okay, let's make it different color. Okay, so you have the red guy, you have number 3, okay, number 4, okay. For number 4 here, it's gonna be also, you can just use the limit comparison, okay. So for this one, it's gonna be combination between geometric series, and it's gonna be the combination between geometric series. Okay, so you see that you have 2n minus 1, that is gonna be the series for p series. I think I said it wrong before. However, it's gonna be 5 to the n. Okay, so that is gonna be another guy. Okay, so for this one, let me reload this one a little bit. Okay, so for doing this one, it's gonna be just, you see that you trying to find convergent for divergent. So you have an equal to this term, right? So it's gonna be, let me just write down to n minus 1, 5 to the n, n squared plus 1. and you're gonna think that, hey, Bn must be the one that can help you adjust the power. And you see this guy is 2n minus 1, so it must be 1 over n. Okay, so you play with me so far. So it's going to be power that is can be reduced. Okay, so this guy is going to become 2n squared minus n over, okay, n squared plus 1, right? And you have the limit equal to what? You have the limit equal to 2 more than 0. Okay. However, you see that you stuck with 5 to the n also. Okay, so you start with 5 to the n. So you also have to include 1 over 5 to the n into this one. Okay, so you also need to include 1 over 5 to the n into this one, and this one will cancel each other out. Okay, so this one and this one will cancel each other out to obtain 2, so that come from the structure of your sequence. And you see that, okay, so we're gonna sin the series 1 over 5 to the n times n, okay, this series, conversion or diversion, conversion, diversion, conversion or diversion, convergent or divergent, and you can conclude that your series to n minus 1, 5 to the n squared plus 1, convergent or divergent. Okay, so I will explain, okay, so I will explain the conversion or diversion for this guy. So for this one, if you look at 5 to the n times n, okay, so if you have 5 to the n times n, let's do it this way. If you have 5 to the n times n, it will be more than 5 to the n for sure, right? Because on the other side, you have multiple of n, okay? And you see that you flip this one, so it's going to be 5 to the n times n smaller than 1 over 5 to the n, okay? And you see this guy, you have this series, okay? So you have this series and this series, and this series turned out to be conversion, okay? So this guy is conversion by comparison test. Okay, so it's gonna be by comparison test. So you're gonna seek conversion, and for the conclusion, it's turned out to be conversion. Okay, so for this one, you use limit comparison, and you're gonna have to test for conversion or diversion of this series by using comparison test. Okay, so that's how we do this one. The last one, okay, the last one, I'm not gonna complete this one for you. However, I'm gonna tell you about the trick a little bit. So you see that this one is look like power. Okay, so this one is look like power. You have n square. So if you try to follow the same trick, you're gonna see that, hey, what could be bn, okay? Because, hey, we have log, which is not constant, okay? So we have problem here. So we have log n, okay? So this one not constant. Can we make it constant? Okay, can we make it constant? Before we know, okay, log n higher than log 2, okay, log n higher than log 2. So you would get 1 plus n log n more than 1 plus n log 2. Okay, so you have 1 plus n log n higher than 1 plus n log 2. And you have everything over n squared plus 4 over n squared plus 4. Okay, so you're gonna test the convergence or divergence for this guy. Okay, so this one will be the series that we gonna use limit comparison. Okay, use limit comparison. Okay, so we're gonna use limit comparison test on this series. So we're gonna just have log 2 at this point, and you see that this guy turned out to be constant, and you'll be able to choose Bn. Okay, so please finish that. This guy will be convergent, divergent, and I will tell you the solution that this guy turned out to be divergent. Okay, so this guy turned out to be divergent, and so the series n equal to 1 to infinity of 1 n log n over n squared plus 4 is divergent by the limit comparison test. Okay, so that gonna be all of the thing that I gonna have. Okay, so it's gonna be two technique on this video. We have the thing that called comparison test, and we're gonna have the thing that called limit comparison test. In order to do limit comparison test, you're gonna have to learn how to adjust the degree, okay, by using this fact. Okay, and you're gonna be able to solve. I would say that it's going to be most of the time, it's not going to cause any problem, okay, for this one. However, if you understand how to like choose Bn and for limit comparison, it's kind of not that hard to do. Okay, so I'm going to stop here.